You figure out where the ESP points to, that is 784 bytes. This return address, don't worry about it for now. We've picked up an address to which we want to make EIP jump to. At the end of this, we put a little knob sled of few bytes just for safety's sake, and then we attach shellcode at the end. The shellcode in this case is 200 bytes of interrupt 3. So hopefully, once this is thrown against peercast, we will be getting a trap to debugger with EIP pointing to the beginning of our shellcode. Now the last piece of the puzzle is, how did we get this return address as 0808FF97? Well, what we did is we search the peercast binaries for occurrences of this opcode, jump ESP or call ESP. We can do it the smart way, like look up the hex opcodes and do a search through it and figure out where the linkages occur, and then from the linked addresses figure out the offset. Or we can do it the easy way using, I won't say donkey way because Metasploit stuff is pretty smart. We'll do it the easy way using Metasploit's elf scan tool. So tools, Metasploit, MSF elf scan. I point it to the file. I have a copy of the peercast binary with me, and I'm looking for instructions which jump or call to ESP. So there I do. I find a few instructions. The instruction that I used is the second in the list. Question, why can't I use the first instruction in the list? 0808FC2F. I deliberately did not use it. The 2F character is actually a slash. And if this is packed within a buffer which goes on an HTTP request, the slash is going to cause the parsing to break. So 2F is a bad character for us. We can't have it as a part of our payload. Therefore, we take the second one. We can't take the third instruction either, because the address of the third instruction is 080900E7. 00 is bad medicine. It's null terminator. It's going to break the parsing. So you have to be careful what to choose. Anyway, I chose 0808FF97. At this location, you'll always find a jump ESP. And when you load up EIP to point to here, you will take the program control to wherever ESP is pointing to. So let's now quickly take a look at this, and then let's try to fit this all into Metasploit. Okay. Let me restart peercast and say /peercast1.pl. This is a request generated, and I'm going to pipe it to peercast. Once I throw it to peercast, on the other window, the response we get is trace breakpoint trap. This is cool. That means we already reached the gates to our shellcode. Let's just quickly look at the core file and confirm this. So say gdb target core.1582. Right. And the error is not SIG-SEGV segmentation fault. It is program terminated with a trace breakpoint trap. All right. So let me look at the registers. EIP is now pointing to some region within my stack. Let me try. Let me also take a look at ESP. If we notice, ESP points to just 2 bytes above where EIP is. So ESP is also very, very near to the shellcode. Let us take a look at the memory from there. Say x64 $EIP. Sure enough, whole lot of interrupt 3s. So this means if we replace the interrupt 3s with our shellcode, we'll get our shellcode to work. There is one slight problem in making all this work. The problem is that ESP, the stack pointer, points very much close to our shellcode. So if our shellcode makes stack operations like call or return, it's going to push and pop the stack, and maybe it'll corrupt our own shellcode. So for us, for making the shellcode run well, we've got to make the stack happy. We'll just chain the stack by 4096 and relocate the stack and then get into the shellcode. So let me show you the next revision of this exploit. Let me restart purecast. So I have purecast2.pl, and here you see this line called my stack happiness. That is the string 81C4 FFEF FFFF44, which translate into these instructions: add ESP, 0xFFFF EFFFF. Why do we want to do this? Let us say if we do a sub ESP, 4096, the word 4096 in memory will be like 0000 something something. Those zeros we can't tolerate. So what we do is we take a 2's complement of 4096 minus 4096, which will be like FFFFFF000. That's also a problem, because we don't want the zeros at the end. So we take minus 4097, which ensures that none of those bytes are 0, and then add a 1 to it. So that's how we arrive at this add ESP, minus 4097, and then increment ESP to get ESPs equal to ESP minus 4096. You will see this string 81C4FFFF prepended to a lot of shellcode. Whenever you see this, it's for stack happiness. Okay. Now, if we do this, it's going to work, and the stack is not going to interfere with our payload. Now, let me actually walk you through let me now switch over from this POC Perl files to actually creating a working Metasploit plugin. Let me quit from this. Purecast is started. Bless you. All right, so let me not get into all this. Some benefits that you get with the Metasploit framework. I mean, if you want to write your POC files, by yourself, you'll have to do all the shellcode manipulation and such. If you integrate it within Metasploit, you can code it for supporting multiple targets. You can choose dynamically shellcode from the generator. You can choose encoding to the shellcode as well. And you can make use of Metasploit's payload handlers, especially when you want to use stage shellcode. You can use advanced shellcode like Meterpreter or VNC inject or find sock shells and whatnot. And basically, you can use this to create a very, very portable, flexible, and a rugged exploit. Quick overview of the framework plugin architecture. This is very conceptual. This is pretty much the same as in 3.0 and 2.6. All the lighter yellow regions are supplied by us. We have to create the stuff in the middle. That is, once we want to create our Metasploit exploit, we have to create a preamble. Then we have to add Perl code to create the payload, and we have to launch the attack by whatever TCP or UDP or whatever vector that is chosen to launch the attack. Once we get the connection, once we launch the attack, we just hand the control back to Metasploit, where Metasploit will kick in one of its own payload handlers. Now for us, we don't have to hardcode the values in our exploit plugin. Values will be supplied at runtime from the framework. What kind of values can we get? User supplied exploit information like what host to attack, what port to attack, what offsets to use if there's peculiarity with kernel A or kernel B, all that stuff. And then we can use the framework to pick encoded shellcode for us from the framework. In 2.6, plugins are implemented as Perl modules. In 3.0, they're implemented as Ruby modules. There is a lot of pre-existing data structures that you get to be used within your Perl module. You get hashes like %info, %advanced, which you have to populate with stuff specific to your exploit. Every Perl module, every plugin has a constructor called new, which will instantiate it. Metasploit will invoke it and instantiate it. And then every module must have an exploit section, which will be called when you launch, when you give the command exploit from within the Metasploit framework to to actually execute stuff. The overall structure of this is you create a package, say package MSF exploit name, you give a name to the module. You have to include the following lines like use base MSF exploit, use strict Perl coding. PEX is the Perl extension routines, extended by Metasploit. In 3.0, you have REX, which is Ruby extension routines. Then you populate these two hashes, advanced and info, with stuff. You create your constructor, and then you have exploit code. Let me actually just walk you through a skeleton Metasploit module. So for peercast, first let me walk you through a skeleton module, then we'll see the specific one to peercast. Okay. So here's actually a skeleton exploit module that I've just written up. You put the name of the exploit at the top. Typically, we don't really use advanced options unless they're absolutely necessary. In the info part, you specify what the name is, what the version is, who wrote it, your script kiddie handle or whatever have you, architecture of the CPU, OS that it runs on, and the priv flag is a boolean. If it is 0, that means you don't get root when you run this exploit. If it is 1, that means you get elevated privileges. The architecture and the OS will be inspected by Metasploit to reduce the available set of payloads for this exploit. I mean, if you've chosen architecture as x86 and OS as Windows, then Metasploit will only show you Windows payloads for your use. Then below you have user options where you will ask the information from the user, what host do you want to target and what port is this thing running on. And some details about the payload, like how much maximum space is available for the payload, what are the bad characters that should never be included in the payload, and if you want to prepend it with any stack happiness. Based on this information, Metasploit will choose a proper encoder for you to create encoded shellcode which does not have any of these unnecessary characters. Then you give a description to this, any references like CVE IDs or bug track IDs or URLs where the advisory was posted for documentation. And later on, you may choose a list of targets that this exploit can work against. I mean, typically there'll be stuff like, kernel 2.2